Yep.
We have a region formed in the xy coordinate plane by two functions, f of x and g of x. The region is bound by the y-axis, the function f of x, the function g of x, and the function's point of intersection, point B. This region is the base of a three-dimensional solid. If the solid is partitioned along the x-axis, its cross-sections are equilateral triangles. This is what a cross-section looks like. If drawn on paper, this is what our cross-section would look like. The base of the triangle is formed by subtracting our two functions, f of x minus g of x, or top minus bottom. This is how we find the height of our triangular cross-section. We cut the face of our cross-section in half to form a 30, 60, 90 degree triangle whose sides lengths have the ratio 1 to √3 to 2. The horizontal leg of the triangle is half the base of our cross-section, or f of x minus g of x over 2. The vertical leg is found by multiplying the length of the horizontal leg by √3 to get √3 times f of x minus g of x over 2. The hypotenuse is found by multiplying the horizontal leg by 2 to get f of x minus g of x. Once we find the legs of the triangle, we know that the height of our cross-section is the horizontal leg of the 30, 60, 90 triangle, square root of 3 times f of x minus g of x over 2. Now to find the area of the cross-section, we first need to find the area of its face. The area of the face can be found by using the equation for the area of a triangle, 1/2 times the base times the height. When we substitute into the equation, we form the new equation, 1/2 times f of x minus g of x times square root of 3 over 2 times f of x minus g of x. When we multiply out our area equation, we get the equation, the area equals the square root of 3 over 4 times f of x minus g of x squared. The square root of 3 over 4 comes from multiplying 1/2 times square root of 3 over 2. F of x minus g of x squared comes from multiplying f of x minus g of x times f of x minus g of x. Now that we know the area of the face of the cross-section, we can find its volume by multiplying the area of its face by its depth, for delta x. Now we can use the volume of one cross-section to find the total volume of our solid. We need to add up the volumes of all the cross-sections from point A to point B. This process is also known as integration. We are going to integrate our newly formed function, square root of 3 over 4 times f of x minus g of x squared, along the x-axis from point A to point B.